then the motion would be much faster. The motion I just demonstrated moved the motor from one point to the other, and it's called point-to-point motion. Now, in many applications, we need a motion that's more sophisticated than that. We need more coordinated motion, and the Galil controller could address that as well. For example, in machine tools, CNC, engraving, you may want the XY motion to move along a trajectory that consists of circles, straight lines, and so on. That mode of motion is possible. In some robotic application, you may want to have a 6 degrees of freedom robot following a certain trajectory. That's easily possible. In some automation applications, you may need electronic gearing. That's possible. In some packaging applications, you may need electronic cam. That's possible. So there are quite a few modes of motion that the Galil controller could supply, addressing the needs of the users. The next function I would like to describe is the stored program in the controller. The controller has a memory allocated for application programs. So I could start with an application program, download it to the controller, and execute it from the controller. This way the host would not be involved in the details of the motion. The host would be free to perform other functions. To illustrate that, let's go to the file here and open a certain program that I have saved in the computer. Let's review it. This is a typical program for a Galil controller. We start with a label to identify the program. Then the next command, PA8000. PA stands for position absolute. It tells the controller, take the motor to the absolute position of 8000. After that, we have the speed command, acceleration, deceleration. The BGX command would start the motion. That's followed by command AMX. This is an interesting command. That's a trip point. It tells the controller, now that you started the motion, wait until that motion is completed. After the motion of X, then there is another command, wait 100 milliseconds. That is, complete the motion, wait 100 milliseconds, and then issue the next command that says, go to the absolute position of 0, which means go back to where you started. Begin the motion, and after the motion is completed, wait 100 milliseconds and jump back to the beginning and repeat the whole process again and again and again. So this program, when it's executed, it would step the motor back and forth 2 revolutions. Right now the program is resident on the computer. I would like to download it to the controller. Download to the controller. Downloading is done. Now to make sure that it's there in the controller, I could list the program. And sure enough, the program appears there in the controller. Now that the program is resident on the controller, I could execute it with the command XQ. And sure enough, now that I have the program executed, the motor moves back and forth. Now, the whole operation at this point is executed from the motion controller. The host is not involved. As a matter of fact, I could disconnect the host altogether. Notice that I pulled the plug on the RS-232 and the operation continues. Now I could put it back. Such an operation is known as standalone because the controller could handle the whole motion and we don't need a host computer. There are many applications where people would prefer to use this mode either for cost saving to save on the computer or for environmental reasons, they don't want to have a computer in the shop. But generating motion, while this is nice, it's not the end of the road. We at Galil have gone an extra step to provide diagnostics. One of the things that interests the user a lot is what's happening behind the scene. That is, when the motor moves, how precisely is it following the target? And how hard is the amplifier working? Is it still operating in the linear mode? Do we have discontinuities and so on? All the diagnostics is available under this function of the storage scope. Let me go to WSTK, click on the storage scope, and now we see that we could display several traces. I'll choose the four scopes, 4 traces. Here with the first trace, we'll display the actual position of X. The second trace, I would look at the derivative of the position, which of course represents the velocity. The third trace will display the position error. That would show us the deviation between where the motor is and where it should be. And for the fourth one, we could select a variety of functions. Let's choose what is called the torque, which is really the plus minus 10 volts that goes from the controller to the amplifier and represents the current going out of the amplifier. Now, if I push the start, it would send the command execute that would start the motion, and then the controller would collect all the data that would be displayed on the screen. So here we go. Notice the motor starts moving back and forth. The program we have is the same one we had before, where the motor steps back and forth 8,000 counts and repeats the motion. And what we see here are the display of the different functions. Now notice the first trace shows the position. It shows that the position starts at 0, moves upward to 8,000, and goes back to 0. Nice. The second trace is the velocity. It's a trapezoidal velocity we programmed with the right parameters, the speed, acceleration, so on. The third trace is the error. It shows that under worst conditions, the error is about 7 counts. And 7 counts with this motor is about half a degree. It happens whenever there is a discontinuity, when we start, when we reverse direction, so the error may be ahead or behind, but once we reach steady state position, either constant speed or stop, the error goes towards 0. Obviously, this is an extremely important function because it shows us how precisely we're following the target. Now, the fourth trace shows the analog voltage going to the amplifier. Typically, the range of this voltage would be between plus and minus 10 volts. Here, we're using something within about plus minus 2 volts, which indicates to us right away that the amplifier is sufficiently large and could handle this motion easily. But the significance of this function is in cases that the amplifier is not sufficient. There could be situations where the motor is working hard and the amplifier gives all it can, and the command goes up to 10 volts and it saturates the amplifier for a few milliseconds. And clearly, if you saturate the amplifier, you're out of control. And the system may be out of control for a few milliseconds, and there is no way to find it out unless you looked at the voltage throughout the whole operation and made sure that it always stays within the linear zone of plus minus 10 volts, preferably within plus minus 8 volts, so you have some voltage to spare. What I've shown here is the ability of the Galil function to tune the system, generate motion, and provide the diagnostics. And between the three functions, we hope that this would help you with your application. Thank you.